The universe's first chapter is written in invisible ink. For over 13 billion years, the story of how everything began has been locked away in the deepest reaches of space and time. We are talking about the cosmic dawn era, that mysterious first billion years after the Big Bang, when the first stars, the first galaxies, and the first black holes flickered to life, tearing the infant cosmos out of darkness. It was a period of such profound and violent transformation that it shaped the destiny of every galaxy that followed, including our own Milky Way. Yet for all its importance, it remains the least understood epoch in cosmic history. By the end of this exploration, you will know the 25 greatest mysteries that define this era, puzzles so profound they challenge the very foundations of modern physics. We will confront galaxies that appear too mature to exist, hunt for stars made of pure hydrogen that were 1,000,000 times brighter than our Sun, and question if black holes could have formed before the stars themselves. What do you believe is the universe's oldest secret? Our journey begins with the very first light in the universe, before planets, before galaxies, even before the elements that make up our bodies. There were only the first stars. Astronomers call them population 3 stars, and they are the ultimate cosmic ancestors. Yet they are ghosts. We have never seen one, not a single direct image of the star that ended the universal dark age. Their existence is a deduction, a logical necessity written into the fabric of everything that came after. The mystery of their true nature is our first and perhaps most profound puzzle. Picture a star, but not like our gentle sun. These were titans, behemoths born from clouds of pristine gas that contained only hydrogen and helium, the two simplest elements forged in the Big Bang. Without any heavier elements to cool the gas and fragment it, these clouds collapsed into singular, monstrous orbs. Current theories suggest they could have been hundreds, even 1,000 times more massive than our own star. Imagine a furnace so vast and ferocious that it burned with 1,000,000 times the brilliance, living fast and dying young in cosmic terms, perhaps lasting only a few million years before a cataclysmic end. Their significance cannot be overstated. Inside their nuclear hearts, for the very first time in history, the fusion process cooked hydrogen and helium into heavier elements like carbon, oxygen, and iron. Then, in spectacular supernova or perhaps even more exotic collapses, they blasted these newly forged seeds out into the void. Every element in your body besides the primordial hydrogen was created inside a star, and the very first batch came from these population 3 giants. So if they were so important and so brilliant, why can't we see them? The answer lies in distance and time. Their light has been traveling for over 13 billion years to reach us, stretched into the faintest whispers of infrared by the expansion of the universe. Our current telescopes simply cannot pick out an individual star from that impossibly faraway era. Instead, we hunt for their chemical fingerprints. Astronomers scour the spectra of the most ancient galaxies we can find, looking for a telltale signature, a severe lack of those heavier elements. Finding a galaxy with almost no metals, as astronomers call all elements heavier than helium, would be the smoking gun that its light comes from a time dominated by those first pure stars. Their violent deaths did more than spread elements, they fundamentally changed the cosmos, heating and ionizing the gas around them and lighting the fuse for the next great mystery. The violent deaths of those first stars did more than seed the universe with new elements, they ignited a cosmic revolution. This is the mystery of reionization, the great relighting of the universe that ended the cosmic dark ages. For hundreds of millions of years after the Big Bang, space was filled with a thick, neutral fog of hydrogen gas. Light from the earliest objects could not travel far, it was absorbed almost immediately, swallowed by the fog. Then something changed. Powerful sources of ultraviolet radiation began to flood the cosmos, and this radiation was so energetic it could strip electrons from those hydrogen atoms, turning the neutral fog into a transparent ionized plasma. Think of it as a billion-year-long sunrise where the fog slowly burns away to reveal a clear cosmic day. The process itself is understood, but the timeline is a profound puzzle. When did this universal dawn truly begin? How long did the sunrise last? And most crucially, what were the primary sources of the light that did the work? The suspects are the usual cosmic pioneers. The first massive stars are prime candidates, pouring out fierce ultraviolet light from their short, brilliant lives. The first galaxies, gathering millions of such stars, would have been even more powerful beacons, but there is a more exotic possibility. What if the primary architects of reionization were not stars at all, but the voracious black holes at the hearts of the earliest quasars? These monsters, consuming vast amounts of matter, can outshine entire galaxies with their intense radiation. The evidence we have paints a confusing picture. Observations of the most distant quasars show us that patches of the universe were already transparent over 13 billion years ago, meaning the fog had been burned away in those regions. Yet, measurements of the cosmic microwave background, the afterglow of the Big Bang itself, suggest the process of reionization was a more gradual affair, taking hundreds of millions of years to complete. How do we reconcile a universe that seems both clear and foggy at the same time in its youth? The answer may be that reionization was not a uniform event. It might have been a patchwork process where bubbles of transparency first formed around the earliest clusters of stars and galaxies, slowly growing and merging until the entire cosmic fog had evaporated. Determining the true timeline is not just about dating an event, it is about identifying the true engines that shaped the transparent universe we see today. But which of these cosmic engines truly flickered on first? This question of the first light sources is not just about chronology, it is about the fundamental character of the early universe. Did it begin with a gentle starlight, a brilliant galactic dawn, or the harsh glare of a black hole's feast? Our telescopes are essentially time machines, but the signals they receive from 13 billion years ago are faint, blended, and incredibly difficult to interpret. The primary suspects each leave a different kind of fingerprint in the ancient light we collect. The massive population 3 stars would have emitted a very specific, intense spectrum of ultraviolet radiation, but their individual light is too faint for us to see directly from such a distance. Instead, we would see their collective glow as part of a small, early galaxy. The earliest dwarf galaxies themselves, collections of millions of these first stars, would be brighter and more detectable. Their light would show the telltale signs of those first heavy elements being forged and expelled. Then there are the black holes, the dark horses in this race. So-called mini-quasars, where a black hole just a few hundred times the mass of our Sun is actively feeding, could outshine everything around them with a fierce, point-like glare. Their light signature would be distinct, often showing broad emission lines from the superheated gas swirling at near light speed before vanishing into the abyss. The challenge is that from our vantage point, these signals are all smeared together by time and distance. A faint blob of infrared light captured by the James Webb Space Telescope could be a small galaxy full of first stars, or it could be dominated by the light of a single voracious black hole. Disentangling these possibilities requires painstaking analysis of the light's color, its brightness over time, and its spectral lines. It is like trying to identify the instruments in an orchestra by listening to a recording played from a mile away through a thick wall and at half speed. The answer matters because it tells us what force truly began shaping the cosmos. If stars came first, it paints a picture of a universe that built itself up from the bottom, with structures slowly coalescing. If black holes were among the very first objects, it suggests a top-down influence where these gravitational monsters could have affected the formation of the very first galaxies around them. The search for the first light is ultimately a search for the universe's original spark. This leads us to one of the most pressing timing problems in all of cosmology. At the centers of the earliest galaxies we can see, we find fully grown supermassive black holes, some containing the mass of over 1 billion suns. These cosmic giants appear in the universe's toddler years, far too soon for them to have grown by conventional means. If a black hole formed from a single massive star's collapse and then ate matter continuously at its maximum possible rate, the physics is clear it simply could not have packed on that much weight in the few 100 million years available. It is like finding a fully grown oak tree in a garden you planted only last week. The existence of these ancient behemoths forces us to confront a radical mystery. How did the first black holes get such a massive head start? Scientists are investigating 3 main possibilities, each more extraordinary than the last. The first theory suggests they skipped the star stage entirely. In the dense, pristine gas clouds of the early universe, a region might have collapsed directly under its own immense gravity, bypassing the formation of any star. This direct collapse would create a black hole seed already thousands of times more massive than one from a stellar explosion, a heavyweight contender from its very first moment. Think of it not as a small sapling growing into a tree, but as a fully formed tree trunk suddenly appearing in the soil, ready to grow. The second theory relies on a frenzy of mergers. Perhaps the early universe was a crowded, chaotic place where smaller black holes, formed from the first stars, constantly collided and combined. Through a rapid series of these cosmic mergers, they could have snowballed into a supermassive object much faster than by simply eating gas. This would be a violent assembly line process, building a giant piece by piece in a cosmic demolition derby. The third idea is the most exotic of all. It proposes that the seeds for these monsters were not born from stars or gas, but were primordial, forged in the extreme conditions of the Big Bang itself. Tiny, dense fluctuations in the newborn universe could have collapsed into micro-black holes. These primordial seeds would have been present from the very beginning, giving them the maximum possible time, the entire age of the universe, to slowly feed and grow. They would be fossils from creation itself, lurking in the cosmic background until galaxies formed around them. Each theory has its own compelling evidence and its own significant challenges. Direct collapse requires very specific, pristine conditions that may have been rare. The merger model needs an incredibly dense cluster of early stars to provide enough black holes to merge. And while elegant, the primordial black hole idea remains highly speculative, with no direct evidence yet for their existence. The truth is, we may need a combination of these processes, or something we have not yet conceived, to solve the puzzle. The formation of the first black holes is not just a question about how they began, it is a fundamental challenge to our understanding of how structure and hierarchy emerged in the infant cosmos. If we cannot explain how these gravitational anchors formed so quickly, we may be missing a fundamental chapter in the story of how galaxies, including our own, were built. That gravitational scaffolding for the first galaxies was made of something we cannot see. The cosmic dawn was built upon a foundation of dark matter, the mysterious, invisible substance that makes up over 80% of all matter in the universe. We know it was there because without its immense gravitational pull, ordinary hydrogen and helium gas would have been spread too thin by the universe's expansion to ever collapse into stars and galaxies. Dark matter provided the cosmic seed, the initial lumpiness that grew into the vast web of structure we see today. Yet this brings us to a profound and frustrating mystery. While we know dark matter's gravitational effect, we have absolutely no idea what it actually is, its fundamental particle nature, and whether it can interact with itself or with normal matter in any way besides gravity, could have dramatically altered the entire timeline of first light. This is not a minor detail, it is the difference between a gentle cosmic sunrise and a sudden, brilliant flash. The leading idea for decades has been cold dark matter. This theory posits that dark matter particles are slow-moving and heavy, interacting only through gravity. In this model, dark matter clumps together first, forming vast diffuse halos. These halos then act as gravitational traps, pulling in the ordinary gas where stars eventually ignite. It is a bottom-up process where small structures merge to form larger ones, and it has successfully predicted the large-scale structure of the universe we observe. But what if dark matter is not completely cold and inert? An alternative theory proposes warm dark matter consisting of lighter, faster-moving particles. This slight difference has a huge consequence. The faster motion would smooth out the smallest clumps, preventing the very first tiny dark matter halos from forming. In a warm dark matter universe, the first structures to collapse would be larger, meaning the first stars and galaxies might have ignited later, in bigger, more massive batches. The cosmic dawn might have been a more synchronized event, with many lights switching on across the universe around the same time, rather than a slow, sputtering awakening. There are even more exotic possibilities. Could dark matter particles interact with each other, creating a kind of friction that changes how they clump? Or, in a truly wild scenario, could some of the dark matter have decayed or annihilated in the early universe, releasing energy that actually heated the primordial gas and delayed star formation? The exact identity of dark matter is not just a puzzle for particle physicists, it is a direct key to understanding the chronology of creation itself. The timing, the brightness, and even the distribution of those first luminous objects were all dictated by the silent, invisible architecture of the dark. To truly see the dawn, we must first understand the shadow it cast. This invisible architecture of dark matter left a faint but universal echo, a whisper from the very gas that would one day form stars. It is called the 21-centimeter line, and it is our most promising window into the cosmic dark ages themselves. This is not light from the first objects, but a primordial radio signal from the neutral hydrogen gas that filled the universe before those objects ever ignited. Every single hydrogen atom in its lowest energy state has a tiny, built-in radio transmitter. About once every 10 million years, the atom's single electron will spontaneously flip its spin relative to the proton. This quantum flip releases a photon with a very specific wavelength, 21 centimeters, which is in the radio part of the spectrum. For the hundreds of millions of years of the Dark Ages, the universe was humming with this incredibly faint radio song, a uniform background tone from the sea of neutral hydrogen. Then the first stars and galaxies began to shine. Their ultraviolet radiation did not just ionize the gas, it also excited the remaining neutral hydrogen, affecting that 21-centimeter signal. By studying how this universal hum was distorted, we can essentially create a three-dimensional map of reionization in progress. We could see the bubbles of transparency growing around the first luminous sources, watching in slow motion as the cosmic fog burned away. The potential is staggering. A successful detection would not just be a single image, it would be a full movie of the universe's first billion years. We could pinpoint exactly when and where the first structures switched on, measure their temperature, and trace the intricate topology of the ionized bubbles as they merged. It would be the ultimate cosmic fingerprint, revealing the detailed timeline and geography of the dawn. The challenge, however, is monumental. That primordial signal has been traveling for over 13 billion years, stretched by the expansion of the universe to wavelengths of several meters. It is now buried under a cacophony of modern radio noise from our own civilization, from our galaxy, and from the Earth's atmosphere. Separating this faint cosmic whisper from the roaring static is perhaps the hardest technical problem in all of observational cosmology. This is the grand mission of projects like the upcoming Square Kilometre Array. Instead of a single dish, the SKA will be a forest of hundreds of thousands of simple radio antennas spread across deserts in South Africa and Australia. By combining their signals, it will act as a single colossal radio telescope with a total collecting area of, as the name suggests, a square kilometer. Its primary goal is to finally hear that ancient song and decode its distortions. If it succeeds, it will not merely confirm our theories, it will transform the cosmic dawn from a collection of faint, mysterious blobs into a richly detailed historical epoch, charted in 3 dimensions across space and time. The silent radio hum of the early universe is not our only source of confusion. A far more dazzling and immediate challenge has just appeared in our newest cosmic snapshots. The James Webb Space Telescope was designed to see the first galaxies, but what it found has sent a shockwave through astronomy. It discovered galaxies that are not just faint, infant smudges. They are brilliant, massive, and impossibly mature, appearing in the universe's first few hundred million years. According to our best models of cosmic evolution, these galaxies should not exist. They are like finding fully formed cities in the archaeological layer reserved for scattered hunter-gatherer camps. This is not a minor discrepancy, it is a direct confrontation between observation and theory, and it forces us to question everything we thought we knew about how galaxies are built. The problem is one of sheer cosmic logistics. After the Big Bang, gravity needs time to pull together clouds of gas, fragment them into stars, and then gather those stars into a structured galaxy. The early universe was a more diffuse place, and the first stars were thought to form at a relatively slow, inefficient pace. Our simulations, based on the well-tested rules of the cold dark matter model, predicted that the earliest galaxies would be small, faint, and chaotic. Yet Webb is showing us galaxies that are hundreds of times more massive than those predictions. Their light suggests they are already packed with billions of stars, and not just young, blue stars, but older, redder stars that indicate a surprising history of prior star formation. How could they have assembled so much mass and forged so many stars in what amounts to a cosmic blink of an eye? Astronomers are now scrambling for answers, and several intriguing possibilities are on the table. The first is that we have misunderstood the efficiency of star formation in the early cosmos. Perhaps in those pristine clouds of pure hydrogen and helium, without any dust or heavier elements to regulate the process, stars formed in a runaway frenzy, converting nearly all available gas into stellar fire at once. It would be a period of explosive, almost wasteful creation. Another idea is that our understanding of the first stars themselves is flawed. If the very first generation of stars were even more massive than we thought, thousands of times the mass of our Sun, their supernova deaths would have been cataclysmically powerful, seeding second-generation stars with heavy elements at a breakneck pace, accelerating the entire cycle of galactic growth. There is a more radical possibility, however. What if these are not ordinary galaxies at all, but galaxies whose cores are dominated by unimaginably bright quasars? A single, feeding supermassive black hole can outshine every star in its host galaxy. If some of these brilliant early objects are actually quasars in disguise, their extreme brightness could be fooling us into thinking they contain far more stars than they actually do. Distinguishing between the light of a billion stars and the light of a single, voracious black hole is one of the most critical tasks for Webb's follow-up observations. Each explanation carries profound implications. If it is about star formation efficiency, we must rewrite the recipe for building a galaxy. If it is about black holes, it means these monsters were not just present early, they were already in control, shaping their galaxies from the very beginning. The brightness of these ancient galaxies is not just a puzzle, it is a beacon, illuminating a potential flaw in our fundamental story of cosmic structure. It suggests the dawn was not a gentle awakening, but a sudden, brilliant flash of maturity we are only beginning to comprehend. These brilliant, ancient galaxies point directly to a second, related gap in our cosmic record. If supermassive black holes grew so large so fast, logic suggests we should find the stepping stones they used along the way. Yet there is a striking absence in the black hole family album. We have catalogued plenty of stellar mass black holes, the remnants of giant stars typically weighing between 5 and 100 times our Sun. And we have found those behemoths at galactic centers, the supermassive black holes with millions or billions of solar masses. But the middle ground, the so-called intermediate mass black holes, are almost entirely missing. This is a profound and curious census gap. Where are the black holes with a few hundred, a few thousand, or even 100,000 solar masses? Finding them, especially in the early universe, is not just about filling a category. It could provide the definitive proof of how the giants grew. An intermediate mass black hole would be the perfect missing link, a clear snapshot of a supermassive black hole under construction. If we could find one in a young galaxy, it would show us the direct path from a small seed to a cosmic titan. So why are they so elusive? Their very nature makes them tricky to spot. A black hole of this middleweight is not massive enough to power a brilliant, galaxy-dominating quasar, which requires a voracious supermassive beast. Yet it is also too massive to be formed by the collapse of a single star, so it lacks the telltale X-ray flashes we see from stellar mass black holes in binary systems. They are the cosmic quiet ones, exerting their gravity without the dramatic fanfare. Astronomers suspect they are hiding in plain sight, in environments we might otherwise overlook. One prime hunting ground is the heart of small, faint dwarf galaxies. Many of these tiny galaxies, which are common relics from the early universe, may host a central black hole that never grew to supermassive status. In these quiet backwaters, an intermediate mass black hole might be the most luminous object, subtly influencing the motions of stars around it without creating a brilliant beacon. Another promising location is within the dense, ancient star clusters known as globular clusters. These spherical swarms of hundreds of thousands of stars which orbit larger galaxies are fossils from the cosmic dawn. Their dense cores are perfect laboratories for black hole growth through mergers. A single intermediate mass black hole could lurk there, revealed only by the peculiar, fast orbits of stars swirling dangerously close to the core. The search is a meticulous one, requiring us to measure the subtle gravitational tug on just a few stars or trace faint X-ray emissions from a trickle of infalling gas. Each potential detection is a major event, a clue to a growth process that has remained hidden. If these middleweight black holes were common in the early cosmos, their scarcity today tells its own story. Perhaps they were all destined to be consumed, drawn into the centers of growing galaxies to merge and build the supermassive black holes we see now. Their absence would then be the signature of a universe that efficiently consolidated its power, leaving behind only the smallest and the largest remnants of a violent hierarchical past. Uncovering them would do more than fill a gap. It would reveal the very rungs on the ladder the cosmos used to climb from darkness to light. The arrangement of these ancient galaxies across the sky holds a secret blueprint. Were the first stellar cities scattered randomly, like lone campfires in a vast wilderness, or were they strung together along invisible threads from the very start? This is the mystery of cosmic geography, and the answer reveals the true architecture of the infant universe. Our most sophisticated computer simulations, built on the cold dark matter model, provide a clear prediction. They show that the first galaxies should have formed at the densest intersections of a vast web-like structure, the cosmic web woven by dark matter. In this view, the earliest lights flickered on along the filaments of this great scaffold, with vast, empty voids stretching between them. It was a universe already showing a preference for community, for connection, even in its first moments of light. But a prediction is only as good as the evidence that supports it. The James Webb Space Telescope's deep-field images are now putting this cosmic blueprint to the test. By staring at a single, seemingly empty patch of sky for days, Webb collects the faintest light from the most distant galaxies, effectively creating a core sample through billions of years of cosmic time. The distribution of those tiny red smudges, each one an infant galaxy from the dawn era, is our first direct map of that ancient geography. The initial results are both confirming and confounding. We do see hints of clustering, suggestions that galaxies were grouping together even in that very early epoch. But the sheer number of bright galaxies Webb is finding also implies a universe that was surprisingly, and perhaps uniformly, littered with star-forming activity. Could there have been vibrant pockets of galactic formation even in regions our simulations predicted would be quiet? This tension between the simulated web and the observed scatter forces a deeper question about initial conditions. The pattern of galaxy clustering is a direct echo of the minute density fluctuations imprinted on the universe in its first split second after the Big Bang. Those quantum seeds stretched across the cosmos by inflation dictated where dark matter would first clump, and thus where galaxies would eventually bloom. If Webb's map of the earliest galaxies shows a distribution that doesn't perfectly match our simulations, it might mean we need to tweak our understanding of those primordial seeds, or more likely, the behavior of the dark matter that sculpted them. Perhaps dark matter interacted with itself in subtle ways, smoothing out the web or creating more small-scale clumps than we anticipated. Or maybe the process of star formation itself was so efficient in certain environments that it lit up regions we thought would remain dark. Every galaxy's position is a data point in a cosmic survey, telling us not just about the galaxy itself, but about the invisible gravitational landscape that birthed it. Decoding this ancient distribution is like finding the original surveyor's stakes for the entire universe. They mark where the construction began and hint at the blueprint the builders were following. The blueprint of the cosmos was written in fire and violence. Those first monstrous stars did not fade gently into the cosmic night. They died in spectacular, universe-altering explosions, and the nature of those deaths is a critical mystery. The supernova of the population 3 stars were not just bigger versions of the stellar explosions we see today. They were fundamentally different, and their impact on the infant universe could have been either creative or catastrophic, a paradox we are still trying to resolve. Picture a star 100 times the mass of our Sun, burning through its nuclear fuel in just a few million years. When its core finally collapses, the ensuing explosion would be something almost unimaginable. Scientists call it a pair instability supernova. In these events, the core becomes so hot that light itself spontaneously transforms into matter and antimatter particle pairs. This sudden conversion robs the core of the pressure supporting it, causing a total, runaway collapse. The result is not just an explosion, but an utter annihilation. The entire star is obliterated, leaving behind no black hole, no neutron star, just an expanding cloud of newly forged elements blasted into the void. The energy released in such an event is staggering, millions or even billions of times brighter than a typical supernova. Now, imagine this detonation happening in a universe that is still mostly dark and quiet, within a fragile, nascent galaxy just beginning to coalesce. What happens next? Here lies the core of the mystery. One possibility is that these supernovae were agents of destruction. The sheer force of the blast wave, traveling at a significant fraction of light speed, could have swept through the surrounding molecular cloud like a cosmic tsunami. It would have heated, shredded, and dispersed the very gas that was poised to collapse into the next generation of stars. In this scenario, a single dying titan could sterilize its local region of space, pushing the pause button on star formation for millions of years and actually delaying the growth of its host galaxy. It was a cosmic temper tantrum of the highest order, but there is a flip side to this destructive power. A supernova shockwave can also act as a trigger. As it plows into neighboring gas clouds, it can compress them, creating dense, rippling shells and knots within the cloud. Under the right conditions, this compression can be the final nudge that gravity needs to initiate a new round of collapse. In this version of events, the death of one generation of stars directly seeds the birth of the next in a brilliant, chaotic cycle of creation. So which was it? Did the first supernova stifle the dawn or accelerate it? The answer may be both, depending on the environment and the exact mass of the progenitor star. To solve this, we cannot look back to that era directly. Instead, we must look around us at the oldest stars still shining in our own Milky Way. These ancient stars found in the galactic halo are the cosmic equivalent of fossils. They formed from gas clouds enriched by just one or two of those first supernova. By dissecting their light with spectrographs, astronomers can read their chemical composition like a history book. The signature of a pair instability supernova is very distinct. It produces a unique pattern of elements, lots of silicon, calcium, and titanium, but very little iron compared to later supernova. Finding a star with that exact chemical fingerprint would be the smoking gun, proving that these titanic explosions truly happened and showing us what they left behind. The hunt is on, and a handful of candidate stars have been identified. Each one is a time capsule, holding within its atmosphere the ashes of a single, catastrophic event from the universe's first chapter. By studying them, we are not just learning how the first stars died, we are learning whether their deaths were a conclusion or a catalyst, a final note or the opening chord of the symphony that built our galaxy. The chemical echoes of those first explosions are not the only primordial force we struggle to trace. We live in a magnetized universe, from the protective field around our Earth to the vast, invisible structures threading through galaxy clusters. Magnetism is a fundamental cosmic ingredient. Yet its origin story is one of the great unsolved puzzles of the cosmic dawn. Where did these pervasive magnetic fields come from? Were they forged in the turbulent hearts of the first stars and galaxies, or were they imprinted on the cosmos by processes far older and more mysterious? This is a detective story with a nearly invisible suspect, for magnetic fields from that era have faded to whispers too faint for our instruments to easily hear. Think of magnetism as a cosmic seed. Today we see it everywhere. It guides the collapse of gas clouds to form stars, it channels cosmic rays, and it shapes the spectacular jets erupting from black holes. But every magnetic field we observe needs a starting point, a tiny initial seed to be amplified over time by the dynamo action of swirling, conducting plasma like a turbine generating power. The question is, where did that first frail seed come from? There are two compelling and very different origin stories. The first is a local, bottom-up tale. In this scenario, the very first stars and galaxies, with their fierce stellar winds and violent supernova explosions, churned the primordial gas. This turbulence, combined with the rotation of the first galaxies, could have acted as a natural dynamo, generating small-scale magnetic fields from scratch. These fields would then be spread and amplified as galaxies grew and merged. It is a story of magnetism emerging from chaos, born from the first acts of cosmic construction. The alternative is a top-down narrative of truly ancient heritage. What if the seeds were planted during the Big Bang itself, or in the hyper-energetic processes of the universe's first second? Quantum fluctuations or phase transitions in that seething primordial soup could have generated feeble magnetic fields that were then stretched across the entire cosmos as space expanded. In this view, the magnetic fields we see today are fossils from creation, woven into the fabric of space-time long before the first star ever flickered. The difference between these two origins is profound. One suggests magnetism is a byproduct of structure formation, emerging alongside light. The other implies it is a foundational property of the universe, as intrinsic as gravity or matter. Solving this mystery is exceptionally difficult because the evidence is so elusive. Detecting the magnetic field of a modern galaxy is challenging enough. Trying to measure the incredibly weak primordial field from the cosmic dawn is like trying to hear a single instrument's note from a symphony played 13 billion years ago, after the music has faded almost to silence. The fields would be billions of times weaker than Earth's, and their signal is buried under eons of later cosmic activity. Astronomers must use extremely indirect methods, looking for subtle effects on the light from the most distant quasars or searching for imprints on the cosmic microwave background. Each potential clue is ambiguous, open to multiple interpretations. Did that polarization in the ancient light come from a primordial field, or was it caused by later dust? The search requires patience and ingenuity, piecing together a history from fragments that barely exist. Unlocking this mystery would tell us if magnetism is a latecomer to the cosmic party or a guest of honor who was there from the very beginning, silently shaping the dawn from the shadows. The violent supernova that seeded the universe with its first heavy elements did more than trigger new stars. They created the very dust that could one day form worlds. This leads to a profound and intimate mystery. Could planets have existed during the cosmic dawn itself? The idea seems almost heretical. Planets, as we know them, are built from the debris of countless stellar generations, from silicon and carbon and iron forged in stellar furnaces. The early universe had almost none of that, yet the laws of physics were the same, and gravity is an impatient force. So we must ask, in that primordial environment with only hydrogen, helium, and the barest sprinkle of new elements from the first supernova, could the process of planet formation have even begun? The journey from stardust to a planet starts with the tiniest of steps. In the cooled ejecta of a supernova, atoms of carbon, silicon, and metals can clump together into microscopic grains of dust. In our later, richer universe, these grains are abundant. They act like cosmic Velcro, sticking together when they collide in the disk of gas and dust swirling around a young star. Through countless gentle collisions, they grow from dust specks to pebbles to boulders, and eventually to mountain-sized planetesimals, the building blocks of planets. But in the cosmic dawn, the scarcity of materials presents an extreme challenge. The dust would have been incredibly rare, perhaps only 1 grain for every trillion atoms of hydrogen. Could these lonely grains ever find each other and stick in such a dilute soup? Some theoretical models suggest it might have been possible, but only under very specific and dramatic conditions. Imagine a massive population 3-star nearing the end of its short life. Around it, a disk of leftover material from its formation might still swirl. When that star explodes in a pair instability supernova, it would not only produce the first heavy elements, but it could also enrich its own surrounding disk in an instant. This would create a localized, dense pocket of dust right where the conditions for planet formation are already in place, a cosmic seedbed suddenly fertilized. In such a niche environment, the process might have kicked off with astonishing speed, forming the very first planetesimals even before the light of the supernova had faded. This raises the tantalizing possibility of population, 3 planets' worlds orbiting those first monstrous stars. What would such a primordial world be like? Without the rich cocktail of elements that make up our rocky Earth, it would be an alien place indeed. A population 3 planet might be a so-called carbon planet with a crust of graphite and mountains of diamond, forged from the predominant carbon output of certain supernova. Or it could be a water world with a mantle of solid ice under immense pressure. If oxygen was abundant in its local mix, it would have no iron core to generate a magnetic field, no silicate rocks like granite or basalt. Its atmosphere would be a thick, primordial shroud of hydrogen and helium, perhaps with traces of methane and ammonia. These would be barren, exotic globes, utterly inhospitable to life as we know it. And their existence would have been tragically brief. Orbiting a star destined to explode within a few million years, any fledgling planet would be vaporized or blasted into the abyss by the cataclysm, its materials recycled into the next generation. Yet their potential formation is not just a cosmic curiosity. It connects the cosmic dawn directly to our own deepest questions. If the planet-building machinery started up so early, it means the universe began assembling the ingredients for rocky worlds almost as soon as it possibly could. Each generation of stars enriched the cosmos further, making planets more common and more diverse. The atoms in our own solar system and in our very bodies were forged across multiple stellar lifetimes, but the process itself, the gentle clumping of dust under gravity, may have had its first tentative trial run in the violent dawn. Finding evidence for such ancient planets is likely beyond our reach, but the possibility reshapes our understanding of cosmic history. It suggests that the path to Earth and to us may have been opened not in a quiet, mature universe, but in the frantic, brilliant, and fleeting moments following the very first light. But if planets could form from the ashes of the first stars, when did that frantic, formative era finally give way to the more familiar universe we know? Defining the end of the cosmic dawn is surprisingly difficult. There was no grand announcement, no final curtain call. This era did not conclude with a bang, but with a slow, cosmic sigh as the universe settled into a new normal. So what actually marks the boundary between that age of first light and the subsequent chapter of cosmic history? The truth is, there is no single, clean cutoff. Different cosmic processes reached their own milestones at different times, making the end more of a fading transition than a sharp line. One candidate is the completion of reionization, the moment when the last pockets of neutral hydrogen fog were finally burned away by ultraviolet starlight. This event, which likely occurred around 1 billion years after the Big Bang, left the intergalactic medium transparent, a state it has remained in ever since. This feels like a logical closing act, as it fundamentally changed how light could travel through the cosmos. Yet, even as the fog cleared, the universe was far from mature. The galaxies illuminating it were still small, chaotic, and furiously forming stars. They bore little resemblance to the majestic spirals and ellipticals we see in the modern cosmos. So perhaps the true end came later, when the first galaxies began to take on more stable, recognizable shapes, when supermassive black holes settled into their cores, and when the frenetic pace of star formation began to be regulated by supernova and black hole feedback. This might have stretched the cosmic dawn's twilight out for another few 100 million years. We might also think of the end in terms of chemical maturity. The cosmic dawn was a period of rapid initial enrichment. The universe went from having almost no elements heavier than helium to having a measurable, though still tiny, fraction of metals. When the process of metal production became more routine, spread across generations of smaller, longer-lived stars, the era of frantic, first-time creation was over. Ultimately, the cosmic dawn's conclusion is best understood not as a date, but as the fading of its defining characteristic, firsts. It was the epoch when everything happened for the very first time. The first star, the first galaxy, the first supernova, the first black hole, the first heavy element, the first magnetic field, and perhaps even the first planetesimal. Once those pioneering events were complete and the universe began operating in a cycle of birth, death, and recycling that continues today, the dawn had passed. Its legacy, however, is written across the entire sky. Every galaxy's structure, every star's chemical composition, every black hole's presence carries the imprint of that foundational era. The choices made in that first billion years, how quickly stars formed, how black holes grew, how elements were scattered, set the course for everything that followed, determining the variety of galaxies and the potential for worlds like our own. The end of the cosmic dawn was simply the moment the universe finished writing its own constitution, a set of physical laws and conditions that would govern the next 13 billion years of evolution. That constitutional document of the cosmos is written in a code of shadows and light. To read it, we must look not at the galaxies themselves, but at the spaces in between, using the universe's most brilliant beacons as cosmic flashlights. This brings us to the intricate mystery of the Lyman-alpha forest, a ghostly fingerprint left on the light of the most distant quasars. As the searing radiation from a quasar journeys for billions of years towards Earth, it passes through vast clouds of diffuse hydrogen gas that float in the intergalactic void. Whenever this light encounters a neutral hydrogen atom, it can be absorbed at one very specific ultraviolet wavelength known as the Lyman-alpha line. But because the universe is expanding, each cloud of gas is moving away from us at a slightly different speed. This stretches the absorption line to a different, longer wavelength by the time it reaches us. The result is a spectacular barcode painted across the quasar spectrum. Instead of one single absorption line, we see a dense, tangled forest of thousands of individual lines, each one a shadow cast by a different filament or cloud of hydrogen at a specific distance along the line of sight. This forest is not a static picture. It is a living record of the gas's condition throughout cosmic history. The shape, depth, and thickness of each absorption line in that forest tells a story. A broad, fuzzy line suggests the hydrogen cloud is hot and turbulent, its atoms jostling violently. A sharp, narrow line indicates a cloud that is colder and more serene. The sheer number of lines reveals the density and clumpiness of the intergalactic medium at different epochs. During the cosmic dawn, this forest would have looked profoundly different than it does today. Before reionization, the space between galaxies was filled with a thick, neutral fog. A quasar's light from that era would show a dramatic, continuous block of absorption, a Lyman-alpha trough, where all light at that wavelength had been completely swallowed by the pervasive hydrogen. As the first stars and galaxies ignited, they began to ionize the gas around them, creating transparent bubbles. The quasar's light would then punch through these bubbles but still be absorbed by the remaining neutral patches. The forest would begin to appear, with its lines growing sparser and sparser as reionization progressed and the neutral fog burned away. Decoding this forest is like reading a complex, multi-layered diary of the universe's adolescence. Each line is an entry describing the temperature, density, and ionization state of a specific parcel of gas at a specific moment in the past. By analyzing the patterns in thousands of quasar spectra, astronomers can reconstruct a three-dimensional map of the cosmic web during the era of first light. They can see where the gas was heated by the first supernova, trace the ionization fronts expanding from early galaxies, and even find evidence for the gentle warming of the universe by those first hard ultraviolet photons. The challenge is immense, a problem of cosmic scale forensics. The signal is incredibly faint, and the interpretation is tangled with complex physics. Distinguishing between a line caused by a small, dense cloud of gas and one caused by a large, diffuse filament requires exquisite data and sophisticated models. Yet, the reward is unparalleled. The Lyman-alpha forest allows us to study the majority of the ordinary matter in the universe, the hydrogen gas that never collapsed into stars, and to witness how it was transformed by the very first luminous objects. It turns the empty space between galaxies into a vast archaeological site, where every shadow tells the story of the dawn that illuminated it. The ghostly barcodes of the Lyman-alpha forest map a universe already growing complex, but one profound question remains almost unaskable. Could the spark of life itself have ignited during that first chaotic billion years? This is the most speculative mystery of the cosmic dawn, a thought experiment that stretches astrobiology to its absolute limits. By our Earth-centric standards, the answer seems a definitive no. The early universe was a hostile, elemental wasteland, lacking the rich chemical diversity we consider essential for biology. Yet the laws of physics and chemistry were operational from the start, and nature is endlessly inventive. So we must wonder, if life is a cosmic imperative, how soon after the Big Bang could it have possibly begun? The obstacles are immense. The first stars lived short, violent lives, offering no stable, multi-billion-year nurturing window like our Sun. Their planets, if any existed, would have been blasted by intense ultraviolet radiation and frequent supernova shocks. Most critically, these worlds would have been built from a severely limited palette of elements: hydrogen, helium, and perhaps a scant sprinkling of carbon, oxygen, and nitrogen from a single stellar generation. Complex organic molecules, the building blocks of life as we know it, would have been vanishingly rare. But within this stark landscape, theorists have identified a few narrow, exotic pathways. One intriguing possibility lies not with rocky planets but with moons. Imagine a gas giant planet, a Jupiter-like world that formed early around a metal-poor star. While the planet itself is a ball of hydrogen and helium, its large moons could have gathered a more interesting mix of ices and silicates from the circumstellar disk. Now place that moon on an eccentric orbit around its giant parent. The relentless, rhythmic gravitational tug of war, a process called tidal heating, could flex the moon's interior, generating enough geothermal energy to melt subsurface ice. This creates a potential habitat, a vast, dark ocean of liquid water, sealed beneath a frozen crust, kept warm not by starlight but by gravitational friction. Such an environment, shielded from lethal radiation and stellar flares, could provide stability for hundreds of millions of years. The energy for life wouldn't come from photosynthesis but from chemistry, perhaps from hydrothermal vents on that alien seafloor where mineral-rich water interacts with hot rock. This scenario pushes our definition of a habitable zone away from starlight and towards gravity. It suggests that life, in theory, might not need a sun-like star at all. It could begin in the eternal night of a subsurface ocean, illuminated only by the faint glow of radioactive decay or hydrothermal plumes. The chemistry within that ocean, however, remains the grand challenge. Could the simple molecules available water, ammonia, methane, carbon dioxide undergo sufficiently complex reactions to form self-replicating systems without the richer suite of phosphorus, sulfur, and metals that later generations of stars provided? It is a staggering long shot, a cosmic Hail Mary, yet pondering it reshapes our perspective entirely. If life could have begun even once during the cosmic dawn, it would mean the universe became biologically aware almost immediately after it became physically possible. It would suggest that life is not a late-stage novelty in an old cosmos, but a phenomenon that emerges at the very first opportunity, whenever and wherever the slimmest window cracks open. While we will likely never find evidence of such ancient, fleeting biospheres, obliterated by the very stellar violence that surrounded them, the mystery forces a humbling realization. Our own story on a world built from the ashes of countless stars may represent not the first chapter of life in the universe, but a later, more refined edition. The dawn may have held experiments in existence far stranger and more fragile than anything we can yet conceive. Our ultimate baby picture of the universe is not perfectly smooth. The cosmic microwave background, that ancient afterglow from when the universe was just 380,000 years old, is the most precise snapshot of cosmic infancy we possess. Its minute temperature fluctuations, mapped in exquisite detail by satellites, tell the story of the density seeds that would grow into galaxies. Yet, within this near-perfect map, there are strange, persistent flaws, anomalies that defy our standard models and whisper of secrets from the universe's first moments, perhaps even from the cosmic dawn that followed. These are not errors in measurement, they are genuine cosmic puzzles etched into the oldest light we can see. One of the most famous is the so-called cold spot, a region in the constellation Eridanus that is significantly colder than our models predict. It is vast, covering an area of sky many times larger than the full moon. In a universe that should be statistically uniform on such large scales, this giant, chilly patch is an unexpected blemish. Could it be a sign of something extraordinary from the era of first light? One compelling theory connects it directly to reionization. If the process of the universe becoming transparent was not perfectly even, if there were colossal bubbles or vast underdense regions where fewer galaxies formed and less heating occurred, it could leave an imprint on how the CMB light traveled to us. The cold spot might be a shadow cast by a truly immense cosmic void, a billion light-year-wide emptiness that formed during the dawn, whose unusual geometry subtly cooled the passing microwaves. Another set of anomalies concerns asymmetry. The universe, according to our foundational principle, should look roughly the same in all directions, but the CMB shows a puzzling lopsidedness. One half of the sky has slightly larger temperature variations than the other, and there is an enigmatic alignment of certain large-scale patterns, nicknamed the axis of evil by scientists, that seems to point in a preferred direction. This is deeply troubling as it suggests a fundamental breakdown in cosmic isotropy, the idea that the universe has no special direction. What if these asymmetries are not from the Big Bang itself, but were imprinted later? The turbulent, uneven end of the cosmic dark ages could be the culprit. If the first stars and galaxies ignited in a great, lopsided wave, if reionization progressed far more rapidly in one part of the cosmos than another due to a chance clustering of the first quasars, it could have created large-scale pressure waves that subtly twisted the fabric of space, leaving a directional fingerprint on the CMB. These anomalies force us to confront an uncomfortable possibility that our pristine baby picture is actually a palimpsest with the violent scribbles of the cosmic dawn written faintly over the original text. Disentangling the imprint of the Big Bang from the imprint of the first billion years is a monumental task. It requires comparing the CMB maps with ultra-deep galaxy surveys from telescopes like Webb, searching for correlations between these mysterious large-scale patterns and the actual distribution of the very oldest galaxies. A confirmed link would be revolutionary. It would mean that the cosmic dawn did not just fill the universe with light, it left permanent scars on its oldest skin, scars we are only now learning to read. These flaws in the cosmic canvas are not mistakes, they are clues, hinting that the universe's first chapters were even more dramatic and uneven than our smoothest stories suggest. The universe's expansion was not a constant backdrop to the cosmic dawn, it was an active player. While dark energy, that mysterious repulsive force, now dominates and accelerates the cosmos, its influence in the first billion years is a profound and subtle mystery. During the era of first light, the universe was still dense, its expansion slowing under the collective gravity of all matter. Dark energy, if it behaves as a constant force as we currently believe, would have been an incredibly faint whisper against the roar of gravity. Its contribution would have been virtually negligible, like a single breeze trying to alter the course of a rushing river. Yet, if we could measure the expansion history of that epoch with impossible precision, we might find a signature of its earliest stirrings, a clue that could reshape our understanding of cosmic evolution. The quest is to determine if dark energy was always a constant, or if its strength has changed over the deep time of the universe. Imagine the expansion rate not as a simple curve, but as a detailed timeline etched by the interplay of two titans, gravity pulling everything together and dark energy pushing everything apart. In the cosmic dawn, gravity held overwhelming sway. This actually helped structure formation. The slower expansion gave gravity more time to pull gas clouds together, to coax them into collapsing into the first stars and galaxies. If dark energy had been stronger back then, even by a tiny fraction, it would have caused the universe to expand slightly faster. That fractional increase in the expansion rate would have acted against gravity's pull, making it harder for those first structures to coalesce. The cosmic dawn might have been delayed, or the first galaxies might have been smaller and more diffuse. So, how do we look for such a minuscule effect across 13 billion years? Astronomers use the most distant objects as mile markers. By measuring the exact redshift and intrinsic brightness of incredibly ancient supernova, quasars, or even the clustering of early galaxies, they can plot the expansion history with finer and finer detail. It is a cosmic archaeology of the vacuum itself. Each data point is a measurement of how fast the universe was stretching at a specific moment in the past. String enough of these points together from the modern era back to the cosmic dawn, and you get a curve, the universe's expansion record. Any subtle wiggle or deviation in that curve, especially in the first few billion years, could be the fingerprint of dark energy behaving differently in its youth. Current observations show the expected slowdown in expansion during the universe's first half, followed by the acceleration driven by dark energy taking over about 5 billion years ago. The data from the cosmic dawn itself, however, remains sparse and incredibly difficult to obtain. The objects are so faint and so far that measuring their precise distances to the required accuracy pushes our telescopes to their absolute limits. Future observatories like the Nancy Grace Roman Space Telescope are designed for this very purpose. By discovering and measuring thousands of the most distant supernova, they will scrutinize that ancient expansion curve for any anomaly. Finding even a hint that dark energy's influence was different during the cosmic dawn would be revolutionary. It would mean this force is not a simple constant of nature, but something dynamic, perhaps a field that evolved as the universe aged. Such a discovery would not just add a footnote to the story of the first galaxies. It would rewrite the fundamental equation governing the cosmos from its first moments to its ultimate fate. The silent push of dark energy may have been the gentlest force in the dawn, but detecting its earliest trace would echo louder than any supernova. The subtle push of dark energy is not the only ghost from the first second that could have shaped the dawn. There is a more tangible, yet equally elusive candidate hiding in the shadows of our theories. What if the dark matter that sculpted the first galaxies was not made of exotic particles, but of ancient, frozen knots of gravity itself? This is the search for primordial black holes, hypothetical relics forged not from dying stars, but from the extreme pressures of the universe's very first moments. If they exist, they could solve multiple cosmic dawn mysteries in one fell swoop, acting as the seeds for everything that followed. The concept is staggering in its simplicity. In the seething, dense plasma of the universe's first second, tiny regions of space could have experienced such intense, random pressure that they collapsed directly into black holes. These would not be the stellar mass black holes we know today. Primordial black holes could have any size, from as light as a small asteroid to many times the mass of our Sun. Their formation would have been a cosmic lottery with density fluctuations as the winning tickets. Crucially, they would have been made of pure, ordinary matter and energy compressed beyond recognition, but they would behave exactly like dark matter, invisible except for their gravitational pull. A universe seeded with countless such black holes would have its dark matter scaffolding already in place from day one, a ready-made framework for the first stars and galaxies to form upon. Their potential role is profound. Primordial black holes of intermediate mass, say a few hundred or a few thousand solar masses, would be the perfect missing link we have been searching for. They could have plunged into the centers of the first gas clouds, providing a massive gravitational anchor that accelerated the collapse into the first stars and galaxies. Even more compelling, they could have been the instant seeds for supermassive black holes. A single, hefty primordial black hole of tens of thousands of solar masses wandering into a young galaxy would not need to grow from a stellar remnant. It would already be a giant in its infancy, ready to feed and become a quasar with shocking speed. This would elegantly solve the timing problem of those impossibly mature, ancient monsters. But how do you hunt for something that emits no light and could be almost any size? Astronomers have devised a clever toolkit to search for these ghosts. For the smallest primordial black holes with masses around that of a large asteroid, one method is to look for their final moments. According to Stephen Hawking's theories, very small black holes should slowly evaporate, culminating in a burst of gamma rays. We have telescopes scanning the sky for such unexplained pinpoint flashes, which could be the last cries of a primordial black hole dying today. For larger ones, the primary tool is gravitational microlensing. If a primordial black hole of roughly stellar mass passes between us and a distant star, its gravity will act as a lens, bending and magnifying the star's light for a brief period. We would see the star mysteriously brighten and then fade in a characteristic pattern, with no visible object causing the effect. Surveys like the optical gravitational lensing experiment have monitored millions of stars for such events. They have found lensing anomalies, but so far not enough to suggest primordial black holes make up a significant portion of dark matter. The most promising modern avenue comes from listening to the cosmos. Gravitational wave observatories like LIGO and Virgo have opened a new window. When two black holes spiral together and merge, they send ripples through spacetime. The masses of the black holes detected in these events are telling. Some fall into a range that is somewhat surprising for standard stellar evolution. Could these be primordial black holes merging in the darkness of interstellar space? The statistics of these mergers, their frequency, their mass distribution, and even the spins of the black holes could eventually reveal a population that was born not from stars but from the Big Bang. The hunt is a process of elimination. Each null result, each failure to find the expected number of lensing events or a clear signal in the gravitational wave data, shrinks the possible mass ranges where primordial black holes could be hiding. So far, they cannot constitute all of dark matter, but they could still be a fascinating component. Finding even one confirmed primordial black hole would be a discovery of Nobel Prize magnitude. It would provide a direct link to the universe's first instant, a fossil from a time before time had any meaning. It would mean that the cosmic dawn was illuminated by structures growing around ancient gravitational scars, remnants of the violence of creation itself. The physics that govern the birth of the first star clusters were unlike anything in the cosmos today. Without the heavy elements we take for granted, the early universe had to build its first cities of light using only the most primitive tools. In our modern era, cosmic gas clouds are filled with microscopic dust grains and molecules like carbon monoxide. These act as a highly efficient cooling system. When a cloud collapses, the dust and molecules radiate heat away into space, allowing the cloud to fragment into many small, dense cores that become stars like our sun. But in the pristine dawn, there was no dust and no molecules beyond simple hydrogen. The only way for a gas cloud to cool was through the faint glow of excited hydrogen atoms, a process vastly less efficient. This changes the entire construction blueprint. Instead of fragmenting into hundreds of sun-sized stars, a massive cloud of pure hydrogen and helium would struggle to shed its heat. It would likely collapse as a single, monolithic entity, fostering the birth of those monstrous, solitary population 3 stars. So how did the first clusters, the ancestors of dwarf galaxies, ever form? The answer may lie in a delicate and violent cosmic dance. Perhaps the first true star clusters were not the birthplace of the very first stars, but their second-generation offspring. Imagine the death of a single population 3 Titan, its supernova blast wave plowing into a neighboring primordial cloud would not only compress it but also seed it with the first traces of heavy elements. Even a tiny sprinkle of carbon and oxygen forged in that stellar explosion could transform the physics entirely. Suddenly, the cloud has access to more efficient cooling. It can now fragment more readily, collapsing not into one behemoth but into dozens or hundreds of smaller stars. A true cluster is born. This suggests a stunning timeline. The first stars were lonely giants, but their spectacular deaths provided the necessary materials and conditions to build the first stellar communities. These nascent clusters, glowing with the combined light of their shorter-lived massive members, would have been the brilliant knots in the cosmic web, the fundamental building blocks that would later merge and assemble into the grand spiral and elliptical galaxies we recognize. Modeling this transition is one of the most computationally demanding tasks in all of science. Simulating the chaos requires tracking the flow of pristine gas, the injection of the first metals, the blasts of ultraviolet radiation, and the shock waves from supernova, all within a cosmos that is itself rapidly expanding. It is a symphony of physics where a single note out of tune can change the entire composition. Did the first stellar cities arise in sudden, brilliant bursts after each supernova, or was it a more continuous, chaotic churn? The answer determines the rhythm of the dawn itself, the pace at which the universe switched from a landscape of solitary beacons to a connected civilization of light. That delicate construction of the first stellar cities occurred within a grand, invisible architecture. The cosmic web, that vast network of dark matter filaments connecting galaxy clusters across the universe, was not a modern feature. Its foundations were laid in the first moments after the Big Bang, and by the cosmic dawn, its ghostly skeleton was already shaping the destiny of light. Visualizing this era reveals a universe in the midst of weaving its own tapestry. Sophisticated computer simulations show us a cosmos not of random scatter, but of intricate connection. Picture a colossal, three-dimensional spiderweb spun on a scale of billions of light years. The thick strands of this web are filaments of invisible dark matter, and at the points where these strands intersect, you find dense knots, the halos where ordinary gas could accumulate, cool, and ignite into the first galaxies. This was the scaffolding upon which the luminous universe was built. The galaxies did not light up in isolation. They were beads strung along the filaments of this great dark lattice, with enormous, empty voids stretching between the threads. The mystery is not whether this web existed our physics demands it, but in directly observing its faint, primordial form. Seeing the dark matter itself is impossible. It emits no light. Instead, we must map it by tracing its influence on the things we can see, the galaxies and the gas. During the cosmic dawn, this task is extraordinarily difficult. The galaxies are incredibly faint and sparsely distributed, like a handful of distant lanterns in a foggy, endless night. Connecting those few dots to trace the filaments between them is like trying to map a continent by the light of 3 campfires. So how do we illuminate the web's ancient structure? Astronomers are pursuing 2 revolutionary paths. The first method uses the galaxies themselves, but in a statistical way. By taking the deepest possible images, like those from the James Webb Space Telescope, and plotting the precise 3-dimensional positions of thousands of the earliest galaxies, scientists can analyze their clustering. Even if the individual filaments are invisible, the galaxies will show a tendency to align along certain lines and cluster at specific distances. Through powerful computers, this pointillist data can be processed to reveal the underlying pattern, the faint outline of the web emerging from the crowd of stellar cities. It is a cosmic connect the dots on the grandest possible scale. The second, and potentially more direct method, returns to the universal hum of neutral hydrogen. Remember the 21-centimeter line, the radio signature of that primordial gas. That gas did not fill space uniformly. It was also pulled by gravity into the web's architecture, meaning it was denser within the dark matter filaments and thinner in the voids. As the first light sources began to ionize the gas, they did so from within this filamentary structure. Future radio telescopes, like the Square Kilometer Array, aim to detect subtle variations in the 21-centimeter signal across the sky. These variations will create a 3-dimensional radio map of the gas's distribution during reionization. In that map, the cosmic web should appear in negative, the filaments traced not by light but by the shadows and echoes in the radio fog as it was being burned away. This would be the ultimate prize, a direct image of the universe's skeleton at the moment it was first being fleshed out with stars. Observing the web structure during the dawn is crucial because it tells us about the initial conditions of the cosmos. The thickness of the filaments, the size of the voids, the spacing of the nodes, all of these are cosmic fingerprints, revealing the properties of the dark matter and the nature of those first quantum fluctuations. A web that forms too quickly or with filaments that are too thin might point to warm dark matter. A web that is more tangled or clumpy than our simulations predict could hint at unknown interactions in the dark sector. This invisible architecture is the true stage upon which the drama of first light played out, and finally seeing it would allow us to read the original blueprint for everything that exists. Every star is a chemical record of its birth. The faintest, most ancient galaxies we can study today hold within their starlight a fossilized echo of the universe's first metallurgy, a baseline of creation known as the metallicity floor. This is not a physical barrier but a fundamental limit, the absolute minimum amount of heavy elements a galaxy can possess. Finding galaxies that brush against this floor is like discovering a language with only a dozen words. It reveals the bare essentials of cosmic chemistry and points directly back to the efficiency of the very first stellar furnaces. The concept is simple yet profound. After the Big Bang, the universe's periodic table had only two entries, hydrogen and helium. Every other element, every atom of carbon, oxygen, iron, and gold had to be forged inside stars and scattered by their explosive deaths. The first generation of stars began this work, but they were few, far between, and incredibly short-lived. Their supernova seeded the surrounding gas with the first sprinkling of metals. The next generation of stars formed from this slightly enriched gas, and the cycle continued. The metallicity floor represents the output of that very first inefficient cycle. It is the chemical residue left after a single round of massive star formation and destruction before any later generations could further pollute the environment. So what does that floor look like in practice? Astronomers measure metallicity as a fraction of the metal content found in our Sun. Our Sun, a middle-aged star formed from gas recycled through many generations, has a relatively high metallicity. The oldest stars in the Milky Way's halo, by contrast, can have metallicities 10,000 times lower. But the true champions of poverty are certain ultra-faint dwarf galaxies orbiting the Milky Way. Some, like the galaxy known as Segway 1, have average metallicities so low they are barely detectable. Their stars contain less than 1,000th of the iron found in our Sun. These galaxies are essentially frozen in time, relics that experienced one brief, initial burst of star formation during the cosmic dawn and then simply stopped. They never grew, never merged, never triggered significant additional rounds of star formation. They are the universe's abandoned first drafts, and their chemical makeup is our closest proxy for the raw output of the first stellar generation. Studying them is a meticulous archaeological dig. By analyzing the light from individual stars within these faint dwarfs, astronomers can dissect their chemical abundances with spectacular precision. They are looking for a specific pattern. The supernova from those first massive stars did not produce all elements equally. Pair instability supernova from the very heaviest population 3 stars would have forged lots of silicon and calcium but relatively little iron. Smaller but still massive first stars that collapsed directly into black holes might have released lighter elements like carbon and oxygen in a stellar wind, but locked the iron away forever. The exact blend of elements we see in a star from an ultra-faint dwarf galaxy is a direct signature of the types of stars that died to enrich it. Finding a galaxy whose stars all show the same peculiar and extremely metal-poor pattern would be the ultimate trophy. It would be a galaxy whose entire chemical history was written by a single, short-lived cohort of the first stars. That pattern is the metallicity floor, the universe's initial chemical signature. Its value tells a story about efficiency. A slightly higher floor would suggest the first stars were incredibly productive, enriching vast volumes of space with their deaths. A lower floor would indicate their influence was more localized, their precious metals falling back into the dense hearts of their host clouds, perhaps even being swallowed by black holes. The metallicity floor is thus a silent witness to the drama of the cosmic dawn. It records not just that the first stars lived and died, but how effectively they managed to distribute their cosmic legacy, setting the initial conditions for all the chemical evolution that would follow for the next 13 billion years. The universe's first chemistry set was bombarded by invisible bullets. Beyond the brilliant light and the shock waves, the cataclysmic deaths of the first stars unleashed a torrent of high-energy particles, the first cosmic rays in history. These were not mere radiation. They were atomic nuclei, protons, and helium cores accelerated to over 99% the speed of light by the immense magnetic fields of supernova blast waves. This was a form of cosmic feedback far more subtle than light or heat. A silent, penetrating rain that could reshape the environment for the next generation of stars. Picture the aftermath of a pair instability supernova. As the colossal shockwave expands, it acts as a natural particle accelerator, far more powerful than anything we could build on Earth. It grabs protons from the surrounding gas and whips them to relativistic speeds, flinging them out into the primordial darkness. These particles become cosmic rays, and their journey is a long one. They do not travel in straight lines. Instead, they spiral along the faint, tangled lines of the earliest magnetic fields, bouncing back and forth, trapped for millennia within the confines of their nascent galaxy or even the local filament of the cosmic web. Their influence is slow, pervasive, and deeply physical. The primary effect is heating. As these high-speed particles zip through the cold hydrogen gas, they collide with the slow-moving atoms, transferring a tiny bit of their immense kinetic energy with each interaction. It is a process of microscopic nudges that adds up to a significant warming of the entire cloud. This gentle, widespread heating could have been a crucial regulatory mechanism. If a gas cloud gets too hot from this cosmic ray bath, it becomes harder for gravity to pull it together to form new stars. In this way, the first supernova might have not only triggered star formation with their shock waves, but also gently suppressed it in their wider vicinity through this persistent particle drizzle, creating a feedback loop that paced the growth of the earliest galaxies. But cosmic rays did more than just warm the gas. They may have been midwives to magnetism itself. One of the great mysteries we discussed is the origin of those first magnetic fields. Cosmic rays could provide a key piece of the puzzle. As these charged particles stream out from a supernova, they constitute an electric current, and any moving electric current generates a magnetic field. This process, known as a Biermann battery, is incredibly weak, but it could create the infinitesimally small seed fields that later dynamos in swirling gas clouds could amplify into the measurable fields we see later in cosmic history. The first cosmic rays, therefore, might not have just traveled along magnetic lines. They could have helped draw those lines in the first place. Perhaps their most fascinating role, however, was in chemistry. The early interstellar medium was a simple place, with molecules like molecular hydrogen being the most complex structures around. Cosmic rays striking these fragile molecules could break them apart or ionize them, creating a soup of reactive ions and radicals. This energetic particle bombardment could have driven a unique and primitive form of interstellar chemistry, forging slightly more complex molecules in the darkness long before planets ever formed. It was a non-thermal chemistry powered not by starlight but by nuclear bullets from stellar graves. This adds a hidden layer to the story of the metallicity floor. The elements we measure in ancient stars were forged in nuclear fusion, but their journey into molecules and dust grains might have been guided and catalyzed by this relentless particle rain. The cosmic rays from the first stars were the universe's first radioactive paintbrush, subtly coloring the processes of the dawn in ways we are only beginning to calculate. Their legacy endures. The Milky Way is still filled with such particles, a faint echo of those first violent accelerators. To understand the true environment of the first galaxies, we must account for this invisible, energetic wind that permeated everything, gently heating, magnetizing, and chemically priming the cosmos for all that was to come. The silent rain of cosmic rays was a subtle sculptor, but the most dramatic relationship forged in the cosmic dawn was between titans. At the heart of the earliest galaxies, we find supermassive black holes. But which came first? This is the ultimate cosmic chicken or egg problem, and its answer defines the very nature of how structure emerged from the primordial dark. Did a galaxy slowly coalesce, its stars swirling together until gravity collapsed a dense core into a black hole? Or did a wandering black hole seed plunge into a cloud of gas first, its immense gravity acting as a focal point to rapidly pull a galaxy into being around it? The evidence we have paints a maddeningly ambiguous picture, suggesting the truth may defy our simple categories. Consider the case for galaxies first. This is the traditional bottom-up view of cosmic construction. In this scenario, dark matter halos form, gathering vast clouds of pristine hydrogen. Within these clouds, the first stars ignite, live, and die, their supernova enriching the gas with metals. Through mergers and accretion, a small galaxy takes shape, its stars orbiting a common center of gravity. At that crowded center, gas densities become extreme. Stars may collide and merge, or massive stars may collapse, planting a small black hole seed. This seed then feeds on the surrounding gas and stars, growing steadily over billions of years into the supermassive monster we observe. This process is logical, step by step, and fits our understanding of hierarchical growth. We see supporting evidence in the modern universe, where the mass of a galaxy's central black hole often correlates with the mass of its surrounding bulge of stars. This tight relationship implies a shared history, a co-evolution where the galaxy and its black hole grew together, each regulating the other through vast outflows of energy. Now flip the script. Imagine a black hole seed already in place, a primordial heavyweight or the remnant of a direct collapse event from the early chaos. This massive object, perhaps thousands of times the sun's mass, wanders through the cosmic web. It enters a large but otherwise quiescent cloud of hydrogen. Its gravity is a powerful attractor. Gas begins to flow toward it, swirling into a vast, hot disk, but not all of this gas falls into the black hole's maw. Friction and turbulence in the disk cause it to fragment, and in these dense, spinning eddies, the first stars are born. In this top-down scenario, the black hole is not a consequence of the galaxy, it is the cause. It provides the initial gravitational instability and the energetic environment needed to kickstart rapid, frantic star formation all around it. The galaxy assembles itself because of the black hole, not the other way around. This idea gains credence from the shocking discoveries of the James Webb Space Telescope. Those impossibly massive, mature galaxies with brilliant quasars at their hearts, all appearing in the universe's first few 100 million years. How could a galaxy grow so large and form a billion solar mass black holes so quickly unless the black hole was there from the very beginning, accelerating the entire process? The James Webb data may be the key that finally picks the lock on this ancient mystery. Its powerful infrared eyes are not just finding these early objects, they are beginning to dissect their anatomy. Astronomers are now searching for a critical signature, the relative ages of the stars in the galaxy versus the activity of its central black hole. In a galaxy-first model, you might expect to see a population of older stars throughout the galaxy, with the brilliant quasar activity turning on later as the black hole finally achieves supermassive status. In a black hole-first model, the quasar could be active from the start, and the starlight we see might be predominantly from a younger population of stars that formed in the turbulent wake of the feeding monster. It is a subtle forensic difference, like determining whether the foundation or the fireplace was built first in an ancient ruin. Furthermore, Webb can study the motions of gas in these infant galaxies. If the gas is swirling in a smooth, organized disk, it suggests a settled structure that formed through gradual collapse, a galaxy-first hallmark. But if the gas motions are chaotic, violently disturbed by powerful jets or outflows from a central engine, it points to a black hole that is already dominant, actively reshaping its home from the inside out. This is not merely an academic debate. The answer rewrites the origin story of every galaxy, including our Milky Way. If black holes came first, they were not just inhabitants of the early cosmos, they were its architects. Their fierce radiation and colossal gravity would have dictated the pace of star formation, the distribution of elements, and the ultimate size of their galactic hosts. They would be the gravitational anchors around which the visible universe crystallized. If galaxies came first, then black holes are a later, albeit powerful, byproduct, a consequence of cosmic structure rather than its cause. The tension between these two ideas lies at the very heart of the cosmic dawn, a fundamental question about power and precedence in the infant universe. As we stare deeper into Webb's deep fields, we are not just looking for ancient light. We are searching for the signature of the original builder, trying to discern whether the cosmos built its palaces around ready-made foundations, or if the foundations were poured only after the walls began to rise. The ultimate fate of those first stars determines the very legacy of the cosmic dawn. While we speak of them as a generation, their deaths were not uniform. Their final moments, dictated by their immense and varied masses, created a cosmic inheritance that shaped everything to come. The leading theory is that the heaviest of these titans, those above about 140 solar masses, met their end in the total annihilation of a pair instability supernova. This cataclysm would have vaporized the entire star, blasting its newly forged elements into the void and leaving behind no compact remnant, no black hole, no neutron star. It was a brilliant final flash that returned everything to the gas from whence it came. But what of the slightly less massive, yet still monstrous, first stars? Stars between roughly 60 and 140 solar masses may have faced a different, even stranger destiny. In this mass range, the core collapse at the end of the star's life is so violent that it might bypass the supernova explosion entirely. Instead of rebounding in a blast wave, the entire core could have collapsed directly, seamlessly, into a black hole. Imagine a star simply winking out of existence, its outer layers falling inward without a spectacular fireworks display. The result would be a black hole seed with a mass of many tens of suns, born in eerie silence. This direct collapse scenario is crucial because it provides a potential fast track for building the giants we find at galactic centers. A black hole born from a first-generation star with, say, 80 solar masses is already a heavyweight contender. It would not need to start from a mere 10 solar mass stellar remnant and slowly eat its way up. It begins life as a substantial gravitational anchor, capable of swiftly pulling in the pristine gas around it. Through rapid feeding and mergers with other early black holes, it could snowball into an intermediate mass and then a supermassive black hole on a timeline that fits the shocking observations from the early universe. But there is a profound and haunting possibility buried within this idea. Could any of these first-generation black holes, forged from the purest hydrogen and helium, have survived to the present day? They would be the oldest discrete objects in existence, silent wanderers drifting through the galactic halo or lurking in the hearts of ancient globular clusters. Finding one would be like discovering a living dinosaur, a relic from the moment light first broke upon the cosmos. The hunt for them is a ghost story written in gravity. We would not see them directly, but we might sense their presence through the subtle, telltale tug on a nearby star or the faint glow of gas spiraling into their unseen depths. Each potential detection is a clue in a 13-billion-year-old cold case. The ultimate fate of the population 3 stars, therefore, is not a closed book. It is an open question that connects the first instant of stellar life to the enduring architecture of the modern cosmos. Whether they vanished in glorious annihilation or disappeared into gravitational graves, their choices in death dictated the resources available for the next generation and planted the seeds for the rulers of the galactic age. The legacy of the dawn is written in these absences, in the elements they scattered and the dark remnants they left behind, gravitational echoes of the universe's first fire. The universe's first chapter seems to defy its own budget. We have tallied the energy output of massive stars, the fierce glare of quasars, and the titanic shockwaves of supernova. Yet when we calculate the total power needed to reionize the cosmos and build those impossibly bright early galaxies, the numbers strain against our ledger. This leads us to the final, overarching mystery of the cosmic dawn. Are we missing a major energy source entirely? Could there be a fundamental astrophysical process or even a new type of object that dominated the early universe and then faded from view, leaving only these profound puzzles as its signature? This is not about tweaking existing models, but about confronting the possibility of a forgotten chapter in cosmic physics. The evidence for a shortfall is circumstantial but compelling. The reionization of the universe required a staggering amount of ultraviolet photons. Our best census of early galaxies and quasars, even with the surprising discoveries from the James Webb Space Telescope, struggles to account for all the necessary ionizing radiation. It is as if we have measured the heat needed to boil an ocean, but can only find enough campfires to warm a lake. Similarly, the sheer mass and brightness of those ancient galaxies imply a frenetic, almost wasteful, conversion of gas into stars that our current understanding of star formation cannot easily explain. Gravity alone, acting on pristine gas, does not seem sufficient to drive such explosive growth so quickly. So what else could have been at work pouring energy into the infant cosmos? The possibilities range from the exotic to the revolutionary. One avenue points to the dark sector. What if dark matter, which makes up most of the universe's mass, was not completely inert? Certain theoretical models propose that dark matter particles could annihilate or decay, releasing a steady drizzle of energy in the form of gamma rays or other particles. In the dense, crowded environment of the early universe, this process could have been significant. This dark energy release would have gently heated the primordial gas everywhere, not in brilliant point sources like stars, but as a pervasive, universal warmth. This background heating could have subtly altered the chemistry of the gas, making it more prone to collapse, or it could have provided the extra push needed to fully ionize the hydrogen, supplementing the work of the first stars and quasars. Another, even more speculative idea involves the stars themselves. We assume the first stars were simply enormous versions of the stars we see today, governed by the same nuclear fusion processes. But what if the physics of fusion in a perfectly pristine environment, devoid of any metals, operated differently? Could there have been a more efficient, or even a more explosive, nuclear pathway that released vastly more energy over a shorter lifetime? Such population 3 stars might have been not just bright, but fundamentally different engines, converting mass to energy at a rate that would make a modern supernova look tame. Then there is the realm of the truly unknown. The early universe was a laboratory of extreme density and temperature, a place where conditions existed that have never been replicated since. Could it have birthed transient, hyper-energetic objects that left no lasting remnants? Imagine something like a supermassive star that undergoes a collapse so violent it triggers a temporary, star-scale burst of energy rivaling a small quasar before vanishing into a black hole. Or consider vast magnetic structures that formed in the turbulent plasma between galaxies, acting as cosmic accelerators that channeled the energy of the universe's expansion into powerful particle jets. These would not be objects in the traditional sense, but ephemeral phenomena, brilliant flashes in the pan that nonetheless contributed a significant fraction of the era's total energy budget. Their fleeting nature would explain why we see no direct evidence of them today. The pursuit of this missing energy is not an admission of failure, but an acknowledgement of the universe's capacity for surprise. Every great leap in astronomy has come from discovering something we did not know to look for. The cosmic dawn, by its very nature, is the epoch most likely to harbor such surprises. It was a unique, unrepeatable phase when the rules were being written, and the first actors on the stage may have been beings we have not yet dreamed of. As the next generation of telescopes, from the gravitational wave observatories listening for crashes in the dark to the neutrino detectors watching for whispers from the past, turn their attention to this era, they will be searching for more than just confirmation of our existing ideas. They will be probing the darkness for the signature of the unknown, for the ghost of a power source that lit the dawn and then disappeared, leaving us with a universe full of wonders and a single haunting question. What else was there? The 25 mysteries of the cosmic dawn are not isolated riddles. Together, they weave a portrait of an epoch defined not by gentle beginnings, but by violent, brilliant, and bewildering chaos. This was not a simple sunrise. It was a cosmic revolution, a billion-year-long storm of creation where the rules themselves were being tested. We have explored stars that were 1,000,000 times brighter than our sun, galaxies that appear impossibly mature, and black holes that grew to impossible sizes in the blink of a cosmic eye. We have confronted invisible scaffolding of dark matter, listened for the hum of primordial hydrogen, and traced the ghostly shadows of the first magnetic fields. Each puzzle, from the metallicity flaw to the missing energy budget, points to a universe that was far more dynamic, far more inventive, and far more extreme than our smoothest models have allowed. This era is not a settled history in a textbook. It is the greatest unsolved chapter in the story of everything. Every mystery we have outlined is a live frontier, a burning question where the difference between a leading theory and the truth is a single, crucial observation. And for the first time in human history, we are building the tools to make those observations. The James Webb Space Telescope is our new eye on the infrared dawn, already upending expectations with every deep field image. The upcoming square-kilometer array will be our ear to the cosmic radio whisper, aiming to map the universe's reionization in 3 dimensions. Gravitational wave observatories are listening for the crashes of ancient black holes, while next-generation telescopes on the ground and in space will dissect the chemistry of the first stars. We stand at the threshold of a transformation. Within our lifetimes, educated guesses will become data. Hypotheses will become confirmed history or be discarded, making way for new and even more wonderful ideas. The cosmic dawn is no longer a theoretical playground. It is a destination, and we are now arriving. So stay curious, watch the headlines. The next great revelation in astronomy might not be a new planet or a distant galaxy, but the solution to a 13-billion-year-old mystery. It could be the definitive detection of a population 3 stars' chemical fingerprint, the first clear map of the primordial cosmic web, or the shocking discovery of a mechanism that powered the universe's first light. The story of how everything began is still being written, and we are all here to witness the next page turn.